Okay, folks, and next we look for a special incarnation of sequences, a special case, which is time series, where obviously we talked about it. The different values in the sequence are associated, the different indices are associated with time slots, or the semantics of these indices are actually time slots. And you see here the agenda. We will briefly talk about time series, and then we will spend a little bit more on pre-processing, because now we can also make use a little bit about this out of this information about these time contexts. We will have a look at similarity models for time series, of course, that should be subsections. We will have simple similarity measures, dynamic time warping, which is a kind of added distance for time series data, and we will also talk a little bit about feature extraction. Why, you will find out that later. We'll probably stop for this week after the pre-processing chapter and have the rest and then spatiotemporal data next week, but we'll see how far it goes. Okay, so before we jump in, let's have a word, a very, very serious word. First of all, most of this content of this subsection, especially of the first subsection, and then on feature extraction, including also many figures, is taken from one very, very awesome tutorial from ADM&ML. ADM&ML is, in Germany we would say, he is the Pope of time series processing, der Papst der Zeitreihenprozessierung. So he, in English we would probably say he's a pioneer in that field, and he did a lot of tutorials, really nice tutorials, and also did a lot of research work, really awesome work also here. So Iman, I'm pretty sure you're watching it. Thanks for all of your emails. Once again, we appreciate your work. Maybe one word, what we say in German, the people that shout a lot lose credibility, and I think that's a pity in your case, because you don't need that. Once again, your work and all the service is really appreciated, what you do. Anyway, if you want to know what I'm talking about, or want to know more about time series, check out Eamon's website. It's really crazy stuff out there. Eamon, I'm really jealous about the engine tuning stuff. Check out the very, very extensive homepage and whatever. Yeah, before we get too emotional about that, maybe we start. Let's have a look at time series data first. So as we said before, time series data is a special type of sequences. So typically the values are now recorded over time. So the sequences represent values that are recorded over time. So what I just said, the index set typically represents specific time points, time slots. And of course we can also say that for general sequences where we don't care basically what the individual values of the sequence are, but in time series where we typically record features, values, numeric values, we distinguish, of course, between univariate time series and multivariate time series. So univariate time series meaning that at each time slot we exactly record one value, and multivariate time series would be we record multiple values per time slot, or a multidimensional time slot, so to say, or feature per time slot. And univariate time series could be stock prices, for example, where we just record the price of the stocks, exchange prices of the stocks. Audio data could be something, maybe not, I don't know. Temperature curves, it's just the temperature. ECG curves, the amount of precipitation from remote sensing devices, whatever. And in multivariate time series, it could be, for example, trajectories, where we record spatial locations like two-dimensional locations or even three-dimensional locations. Per time slot we have three values, not only one value. Video data, for example, if we encode all the videos, all the images of the videos as color histograms or other stuff, of course. And then, of course, combinations of these sensor readings from above. So those are multivariate time series. And they have, multivariate time series is, of course, the more general concept, and most of the concepts we're talking about will be presented for the univariate case but can be just for clarity reasons, for ease of presentation. But of course, it can be applied to multivariate time series quite easily. Yeah, just that you have that in mind. Okay, so we'll start with pre-processing, and pre-processing is very often very important for time series. It's just because in sequence data we typically have categorical values, so sequences over categorical values. In time series data we typically have a lot of sensor readings, numerical readings from some devices that automatically generate data, like those here. And very often we have a lot of noise in that, or the calibration of the sensors is not perfect, or stuff like that. And in order to somehow make the individual time series more or better comparable to each other, we rely on pre-processing, and we'll talk about that now in the first subsection here. So pre-processing is typically involved in order to clean the data, especially to remove artifacts, distortions, noise, or whatever. And we can do a lot of pre-processing, and this is a kind of alert here. First of all, a warning. Pre-processing is extremely application specific. I hope that will be clear when we talk about the different things here. But sometimes in some application you really want to remove distortions, for example, or artifacts. In other applications you are especially interested in those artifacts. Yeah, so you have to really think about what you are doing in data pre-processing. Data pre-processing, have the big picture in mind about this data science or KDD process or whatever. We're talking about the steps before we do the data mining. So always be aware about this shit in, shit out problem. If you do data pre-processing and generate shit, you will get shit out. Yeah, even if you apply the best machine learning or data mining stuff. That's clear. Yeah. Okay, so the first pre-processing I want to show you here is offset translation, sometimes also called shifting. There are other terms or names for that, but that is hopefully or most likely the terms that are most frequently used. So you see that here the time series, the red one and the blue one, they are pretty similar, but they have different offsets, different scale, so to say, in the values that they have. So the shape is extremely similar. It's probably the same, not exactly the same, but pretty similar. But they have different offsets. And in that case, what you can do is you can move each time series by its corresponding mean. So you see that here we have the red one from above, and we have the blue one from above. And if you compute the mean of all the values that you have in Q and all the values that you have in O, which gives you the mean of Q and the mean of O, and then transform Q by subtracting its mean and O by extracting the mean, you see that the mean of both of those curves will be at the 0 line now, according to the offset, or in the context of the offset. So the mean will be 0. So the time series now, since they have more or less the same shape, will now be considered to be very, very closely related or very, very similar. And that is different to this one here, obviously. So offset translation using the mean could be a very, very good point or very valuable pre-processing step to make different things that have maybe a different calibration in the sensor or stuff like that comparable. But once again, maybe it's not the best way in all applications, as you see, as you can imagine probably. Okay,